All right, welcome to 10-4-18-6-18. Today we're going to be picking up where we left off, which was sort of mid-sentence in a description of learning to search algorithms. And so today we'll be sort of wrapping up that meta-algorithm that we kind of began our discussion with. And then we'll be thinking much more in detail about the possible scoring functions that we could actually use within such a meta-algorithm. Okay. So this is just a reminder about homework 1. I'm probably not going to get all the way through the remainder of learning to search all of RNNs, random neural language models, and seek-to-seek models today. If we do, maybe we'll just release homework 1 today. Since I probably won't, we'll probably hold off until releasing it on Wednesday. And yep, so that's the only detail there. And so I want to turn back to our discussion of learning to search here. And in particular, I want to circle back to a topic that's really important, which is how to actually construct scoring functions for the running example that we've been using, which is part of speech tagging. So we'll get to a fancy way of constructing such scoring functions, but it's useful also to have in mind what people were doing, say, before seek-to-seek models became prominent in sort of the early 2010s. Okay, and that was relying on linear models. Okay, so before we even jump in here, let's actually just look back at what we were doing last time. And so you'll remember that we had this picture of sort of a search space for part of speech tagging that was specific to the actual input, right? So flags like a plant was our input sentence, and we induced this search space, which was a directed acyclic graph, where each state represented a partial tagging of the sentence. And so the question is, how could we construct a score for one of those partial tags? And one way of actually going about that would be to use a linear model where we have some features of that path, and then we just have a weight vector. And so to get the score, we just take the dot product of the features with the weight vector. Simple idea. Now we just need to come up with some features. So what could those features look like? Well, for this sentence, time flies like an arrow, one thing that we could do is we could say, well, we're going to look at the number of times that the tag P appears as the tag for the word like. Okay. And we could say that there's going to be some weight attached to that particular feature. So if you've seen HMMs before, this should ring sort of very familiar, because you can think of this as like an emission probability on an HMM. Okay, so the other thing you could do is you could just have a feature that is the number of times that P appears, right? A count of the tag P by itself. You could also do something fancy, which would be the number of times that the tag P occurs in the middle third of the sentence. Okay, so we could count up the number of words, we could figure out where P is and how many times it's appearing there. We could also start to count tag bigrams. Like we could look at, because remember, if we're at a partial tagging of the sentence, then maybe we've already seen this entire sequence of tags, right? This could be like some path through our search space. And of course we can see the entire sentence, right? Because it's not changing as we're moving through the search space. So you could then have the number of times that the tag bigram VP appears. And this should sort of also feel familiar if you've done HMMs. It looks kind of like a transition probability. Okay, but then you could have those transition probability-like things also look at the sentence simultaneously. So you could have a feature that fires if there's a VP and it's followed by the word and. Sorry, the highlight's a little off here. Okay, and then we could have the tag bigram where P is the tag for the word like, right? This is kind of a combination of an emission and a transition probability into one. And maybe something that looks at whether the words are lowercase, right? And so this goes on. The count of trigrams, NVP, right? We'll actually talk about n-gram models. I'm going to kind of skip that. You could also have the number of post-verbal nouns, right? This is sort of a linguistic notion of nouns that come after some verb. And it's natural to actually have lots of these in languages that are in subject, verb, object order. So it's a reasonable feature. We'll skip this discussion of finite state transducers. So you can think of essentially these attributes of the tag sequence in the sentence as being computed at each position in that XY pair. And in our case, you could think of it as being computed on any of the partial tagging that you've seen so far. Okay. And so if we think of this in terms of a particular tag at position I, then all of those examples that we looked at, we could articulate via some template, some notion of a template that looks at the full name of the tag, the first letter of the tag, the full name of the previous tag, the full name of the word at that position, the last two characters of the word, the first four characters of the word, and so on. These are sort of getting at suffix and prefix features, right, that actually understand something about how verbs are conjugated or something like that, or lemmas of words. Okay, and so all of these would provide you with potential features that could fire, and then we can actually combine individual examples from that previous list and conjoin them into feature templates. So you might want a template that is a feature that fires on the previous tag, the current tag, and say the suffix, the last two letters of the word that's coming, right? Okay, and so all of these would allow us to kind of build up this rich feature set so that we can then use these templates in the actual sentence wherever we are in our search space, right? So if the template was looking at, say, this previous tag, the current tag, and the suffix, then you could look for, say, the first two words you could have noun and verb are the previous tag and current tag, and then the next word is the word like. Again, so our highlighter is off. So the point is that then once you have all of these features, you can, for each feature that fires, you can multiply in its corresponding weight in the linear model, and that gives you a score of the quality of that path. Okay. So very quickly, you could easily end up with millions of features here, right? And this is just supposed to be our simple example of part of speech tagging. Okay. Imagine if we were actually doing machine translation or acoustic speech recognition or image captioning, the examples that we're going to get to later. Okay, so back to learning to search. Now that we have some notion of how we could actually score these paths, let's think about that meta-algorithm that we had introduced and how to specialize it so that we can get two algorithms that we'll talk a lot about, which are sort of the traditional supervised imitation learning and Dagger. Okay. So here's our meta-algorithm from last time. And so you'll recall that in this meta-algorithm, we said that we have some training data set, and it's going to consist of XY pairs in the data set B. And the first step of the learning algorithm is going to be to induce our graph from X. And then we're going to come up with some scoring function, like that linear model, that maps from particular states in our search space to scores. We'll also have some cost function, C star, that is our oracle completion cost function that tells us from any state what is the best that we could possibly do in terms of cost from that state. Okay, so then we'll gather a trajectory of states. We'll construct training examples that consist of pairs of states in our search space with the oracle action that would be taken at that state if we had perfect knowledge of what the correct answer was. And then we'll update our parameters of our scoring function so that they do a better job at imitating that oracle policy. Okay, so this whole algorithm is sort of a meta-algorithm for imitation learning. And the notion of imitation here is that we want the policy that we learn, which is going to be based on that scoring function, to do almost the same as the oracle policy in terms of its behavior. Okay, so we're going to update the parameters of the scoring function so that it matches the behavior of the oracle policy as well as possible. Okay, so now let's actually look at a concrete example with part of speech tagging. Okay, so we're going to say, first talk about algorithm number 1, which we'll denote by sort of the traditional supervised approach. And here, we'll say that what we're going to do is let that step 4 above be done with the oracle policy top, sorry. Oh, and I guess I forgot kind of an important detail here, which is what does this meta-algorithm return? Does anyone have any thoughts on what should we write here that the meta-algorithm is actually returning? Say it again? The parameters theta, and what if we wanted an actual policy? Which policy should we return? So the scoring function is going to tell us the actual scores on the edges, but what would a policy be that could rely on that scoring function?
Policy can make the score biggest.
Yeah, the policy that makes the score biggest.
Yeah.
So one of the policies that we had talked about last time was this notion of a greedy policy, right? Which chooses the highest scoring nearest neighbor, right? And so we could say we return the greedy policy induced by S theta. And we could call that some phi hat. So this greedy policy, if S theta were the negative of C star, okay, let me actually write that down because it's such a tricky little question to say out loud. So if S theta equals negative C star, what is pi hat? Yeah, it's just the optimal policy. It's the oracle, right? Okay, so in general, we won't know what C star is, except on the training examples, right? So at test time, our S theta won't equal negative C star, but hopefully, we hope that it will have learned to behave similarly to C star, and we'll predict something that's at least close to pi star. Okay. All right, so the first algorithm here is we're going to let step 4 be done by the oracle policy. And so we could say that, as an example, we'll consider POS tagging. And so you could think of, again, that sentence flies like a plant, corresponding to a search space that has some start node. And this time we're not going to draw out the entire search space. We'll just look at some salient parts of it. So, namely, flies could either be a noun or a verb. And what we're going to be concerned with is the actual path in the search space corresponding to the ground truth, right? So the ground truth here is noun, verb, right? Determiner, and then noun. Okay. So this path corresponds to the ground truth, and we could actually think of how to use that path to generate our training examples. So according to the meta algorithm, we've just collected a trajectory, right? From start to end to verb to determiner to noun. And the question is, what do our training examples look like for this case? What does step 3 return?
Only the nodes and the actions of the green path.
Yeah, exactly. It's just the nodes and the actions that we took. So, so the first training example is just going to be this start node followed by noun, right? And then we could label some of the other states so that we can actually refer to them properly. So we could call this S1 and this S2, S3, and S4. And so then we'll have another training example that is S1 and verb, right, where this is state S1. And then we'll have another training example that is S2 and determiner. And then we'll have another that is S3 and noun. And then we're done. And if we wanted to, we could have sort of an extra end state, just so we're a little bit more symmetrical. And then in that case, we could have S4 end. Yeah.
When you say step 4, do you mean step 2, like gathering the trajectory instead of the optimal oracle policy?
Oh yeah, sorry about that. This is step 2. So here we're trying to decide how to actually collect the trajectory. And so we're just saying that the way that we're actually going to gather the trajectory is by using the oracle policy. Okay, so once we do this, we can now train that scoring function so that it does a good job of predicting a high score for the corresponding action, right? So when we're in the start position and the sentence is flies like a plant, it should have a high score. We should update the parameters theta so that whatever our features are, they give higher weight to n rather than v. And then when we're in state S1, we're going to update the parameters to give high weight to action v instead of n. And so on down the line, so that we're gradually increasing the scores of on these edges. And so if we actually wrote in, maybe what the scores were as we were going along, maybe initially this is actually a low score. So maybe this has score -3, and this has high score of 4, right? And say over here, this has low score and high score. So here we have, say, high scores, and then this one maybe again is say a low score to a high score. And so you can see that the actual model, based on those scores, if it were using the greedy policy, would have actually made errors at several different places along the way, right? It would have made an error here, and it would have made an error here, and it would have had to sort of randomly break a tie in these three in the middle. So there's lots of places where it would have been making these little errors, and the question then becomes, how do we actually update the scoring function to give higher weight to the correct path? And we can do that once we actually have the training data in which to update the scoring function. Okay, so this seems like a pretty simple learning algorithm, but there's sort of one main issue. Can anyone think of what that issue might be? Yeah.
We're not learning any bad examples, so if this is an example that the system knows, but if there's any test case where it hasn't been received that sequence, then it might end up giving the wrong outcome.
Yeah, so in particular, we could say that the model, or the classifier, let's say the scoring function even, meaning S theta, is never exposed to its own mistakes. Right. So at the beginning here, it looks like the model really wanted flies to be a verb. Okay. So if a new test example came along, and we hadn't updated the parameters enough to give n high weight over v, then the model would have immediately gone down this v path. And at that point, the model might have no idea how to actually recover. Okay, so this is such an important problem that it has a name. This is called exposure bias. And one way to actually kind of conceptualize this is to think in terms of a totally different example, which is Mario Kart. We'll look at this example in more detail in a moment, but basically you could imagine in Mario Kart, if you wanted to learn a policy that was able to drive a little cart through a course, there's a beautiful depiction of a course, and you could imagine that maybe the oracle policy would just stay in its lane and drive correctly through the road. Okay, but what if the model's behavior was initially similar, but then it kind of like veered off? So at this point, at this moment, the model might actually have no idea which of these paths, these sort of completions of this trajectory, are the best. Because if this is pi hat, it might have never actually seen this sort of blue behavior before. Okay. And so we could say that in this case, pi hat never learns what to do when it's near an edge. It's just not even sure how to actually recover. Okay. So how do we actually solve this problem? Well, the answer is just to replace step 2 with a slightly different option than the oracle policy. Okay, so here's algorithm number 2. And this is Dagger, which is sort of a funny abbreviation for dataset aggregation. Okay. And so in this algorithm, what we're going to do is we're going to say let step 2 here, oops, be done by not the oracle policy, but by our model's current policy, which we could call pi hat. And just so we're abundantly clear here, what we're saying is pi hat is going to take in a state and it's going to return the argmax over all possible actions scored by our scoring function that takes in the state and action pair. So our action is from some, say, set of actions. Okay. So if we do this, we can kind of think about the example that we were just looking at and sort of consider how the behavior of this algorithm gives us a different set of actual training examples. So namely, we could say that if we take this guy, now what we want to do is just update this picture with how it would actually behave if we were instead using our models policy. Okay? So what we could see here is our training examples. We can sort of remove those old training examples that we were working with. And we're also going to have to flesh out a little bit more of the actual graph here, right? Because our model is not going to behave the same way. So specifically, the first thing that our model is going to do differently is it's going to take a step down this path, right? Because it has higher score. From there, it's going to have a couple options in front of it, like noun and verb. And then from there, let's suppose that it selects verb. Well, then again, we have the same options as before here, noun, verb, determiner. And if it selects determiner, then it'll have options N and V. Okay, so here what we're looking at is that the model policy is selecting a different way of actually completing this path. Okay, and so what our training examples could look like here would be similar to what we had before, but let's actually come up with some new state names. So let's say that this is state S1 prime, and this is S2 prime, S3 prime, and S4 prime. Okay, so put this up here. So now our training examples are going to be slightly different, right? We're going to say, okay, as before, we have that same start N training example. Okay, but then we're now, because we're going to follow the models policy, we're going to have an example S1 prime, and then verb. And then we'll have S2 prime, determiner, and S3 prime, noun. And finally, S4 prime, or we could say this reaches substance state. So here, the collection of training examples has changed such that now, when we make the initial mistake of labeling flies as a verb, we can recover and still do well at tagging the rest of the sentence. Okay. And remember why this is important. The scoring function is going to have features that look back at all of those other aspects of the path up until now. So it's going to be counting things like the number of nouns that occurred before, right? And so it's actually, without this training method, it would be really difficult for the model to learn that when you have this verb here for flies and you see the like, it's actually difficult in English to have two verbs following each other. So we're going to actually have to learn that sometimes our model makes mistakes and we might need two verbs following each other in this particular form to actually correct for that mistake. Okay, so there's a couple really important things going on. I guess one is here where it learns the correct action, even if it makes a mistake. And then second, it's going to sort of, through all of these other training example, it also learns to correct for its mistakes. Oh, sorry, I actually have my arrows wrong. So the place where it's going to learn the correct action, even if it makes a mistake, is in this first case, right? So the place where it made a mistake was the model predicted verb, but the actual thing was noun, okay? So the training example still contains the action of the oracle policy, right? Because we know what the true sequence is, right? In this case, we have some y star sitting here, right? This was our vector x, and this was our training example y. And so we know that n, the determiner verb, was the correct sequence. And so we're going to try to imitate that sequence as well as we possibly can. Okay, so the last detail is that, so the actual algorithm is going to use a stochastic policy that mixes pi star and pi hat. So what it will do is, in the end, sort of behave somewhere in between the oracle policy and the current greedy policy. Okay. And so I guess the last detail here is that sort of the main takeaway is that this algorithm is going to have theoretical guarantees that it will learn a policy that has sort of low regret in hindsight. So the theoretical guarantees are actually quite strong here. So let's look at those. Okay, so here's the first sort of important detail, which is about the notion of stochasticity that we have here. So Dagger is going to assume that we follow a stochastic policy that flips a weighted coin, where the weight on that coin is some beta I at time step I. Okay, and it will use that weighted coin flip to decide between the oracle policy and the model's policy. So we can write this in sort of this notion of sort of a mixture of two policies to say that the policy pi I is our policy at time step I. And it will be, if beta I here was 70% oracle, then 70% of the time it's going to follow pi star, and 30% of the time it's going to follow pi hat. And so the requirement is that that sequence of beta 1, beta 2, beta 3, all the way through each of the time steps of our learning process is chosen so that the sum of that sequence goes, or sorry, the average of that sequence goes to 0 as the number of training iterations, n, goes to infinity. So this is number of training iterations. Okay. So okay, so we just need some mixture of these two. Can you guys come up with some actual sequences, some mixtures that would give us this nice property? Yeah.
It is sequence like half, 1/4, 1/8, goes
Right. So 1/2, 1/4, 1/8. So can anyone articulate that sequence as in terms of I?
Exponentially decaying.
Yeah. So we could have this exponentially decreasing sequence, right? So we could raise say, some probability like 0.5 to the power I, and that would give us back exactly 1/2, 1/4, 1/8, if we started with 1/2 to the I. Okay. So that's a good sequence. Any other sequences we could use?
1 over n squared.
Say it again.
1 over n squared.
Yeah, so if we have a term that is 1 over I squared, that would also ensure this. Any really sort of stupid simple sequences that we could use? I want you to observe just how lenient this requirement, so to speak, is. It's like the simplest possible sequence we could do.
Beta I is equal to 0.
Yeah, we could just have beta I equal to 0. We could just follow our model's policy the entire time. Okay, here's another one, and in some of the experiments that we're about to look at, we're going to actually use this. So this one is beta 1 is equal to 1, and then beta t is equal to 0 for all t greater than 1. Okay, so you could use the oracle policy for, say, the first maybe epoch of training, and then we could switch to the model's policy after that. Okay, so all of these are valid policies according to Dagger, and the question is, why do we care about these? Well, the reason is that Dagger comes with these really strong theoretical results, and that is part of the reason that we're talking about this particular algorithm, as opposed to the sort of myriad of other learning to search algorithms out there. So one is, the first point to make is that the theory kind of mirrors the intuition that exposure bias is a bad thing, okay? And so we can sort of see this played out by looking at two theorems, one for that supervised approach that we just looked at, and one for Dagger. Okay? So the high-level picture is that for the supervised approach, the theorem that we get shows that that learning algorithm performs okay, and that is when we're using the oracle distribution over states. Okay. And by okay here, we mean that it's going to actually give us sort of the number of mistakes is growing quadratically with the length of the actual decision sequences that we're making, sort of the lengths of the paths, let's call that T, and the actual overall classification error that we see on our training data. Okay. So here, what we're looking at in this theorem 2.1 is an expectation over states according to some distribution d pi star. Okay. D pi star here is just the distribution over states if you were to follow the oracle policy. Okay. So there's something kind of tricky going on in this theorem, which is that their notion of a distribution over states is also tied to a distribution over pairs or over instances x, right? So we kind of have to assume that the x's are sampled from some p star, and then we induce gx from x, right? So this is step 1, step 2, step 3, and then induce this distribution d pi star from gx and some labeled or some ground truth y, okay? Where d pi star is what we should have done on that example. Okay, so even if the distribution over states is exactly the same as it is at training time, we still kind of get this lousy bound that we're only able to bound the number of mistakes that it's making quadratically in the task horizon. Okay, so by contrast, for Dagger, we have a similar bound, but here there's no t squared term. We're actually linear in t. And not only that, this second theorem is for the case where our distribution over states is our test time distribution over states. And so what we're saying is that at test time, the number of mistakes grows linearly in the task horizon and the classification cost steps. Okay, so how they actually get these results is kind of interesting. I'm not going to go into great detail here, but I just sort of want to highlight the general approach, which is that it actually relies on a reduction of structured prediction to no-regret online learning. So it turns out there's a lot of people who have sort of studied in great depth this general problem of online learning, where you sort of make a decision, you take some action, and then based on that action, you receive some loss. Okay? And so there's this general class of no-regret online learning algorithms. One of them is hopefully an old favorite of yours, which is called online gradient descent. You all know it by the name stochastic gradient descent. And if you use an algorithm like that one, you can ensure that you'll get back a sequence of, this is actually a statement of defining what a no-regret online learning algorithm is. So the idea is that it will produce a sequence of policies, pi 1, pi 2, up to pi n, right? Where you could think of these as the policy after 1 training iteration, after 2 training iterations, 3, 4, and so on. And it's going to ensure that the average regret with respect to the best policy in hindsight goes to 0 as the number of training iterations goes to 0. Okay, so this is actually an incredibly strong statement. What it's saying is that the difference between the actual average loss and defined by the expected loss of our model. And so long as we are following the actual distribution induced on that search space by our model, then we get that no-regret online learning guarantee.
Question.
Yeah.
The capital pi, how do we interpret that? Is it going to be a collection of all
Oh,
policies?
yeah, sorry about that. So capital pi here is the set of all possible policies that exist in the world, right? So for a search space, if the search space itself is finite in size, then you could actually enumerate every possible policy, right? Because there's finitely many states in that search space. And for every state in the search space, the policy has a specific action that it takes. Okay, so so those are for deterministic policies. There could also be stochastic policies, where at every state we have a distribution over possible actions. So this is considering every single possible policy that exists, right? We can't actually enumerate them, but what we're saying here is that the theoretical result says this sort of unknowable quantity, right? The difference of the knowable quantity, which is our average loss during training, and the unknowable sort of best we could have done is going to go to 0. Okay, so that's actually an incredible result. Okay, what about some empirical results? This lecture would not be complete with a Mario Tuxkart video, so let's see if we can get this to work. Okay, so this is Mario Tuxkart, and this is at first going to be a sample from an actual expert trajectory. So this is someone who's really good at this game playing it, okay? And okay, they're going to do really well. They're going to stay on the track. It's kind of uninteresting. Let's jump ahead. So now we're going to look at what happens when we take that supervised approach to training after 20 laps of training. Okay, so this is the supervised approach. It was only trained, oh, it fell off. Okay, it's back on. Let's see if it does a little bit better here. Oh, it's near the edge. Oh, it fell off again. Okay, now it's gonna do a little bit better, I think, this time, because it's got a little bit of training. Okay, it's staying centered, pretty good, looking good, and so at this point, seems pretty good. Oh, except it went near the edge again, and it didn't know what to do because it had never been near the edge. So time and again, this policy gets near the edge, it freaks out because it has no idea how to behave, and it does terribly. Okay, so now let's jump to the performance with Dagger. SMILE is a different learning to search algorithm. Okay, so this is Dagger after 20 laps of training. And here again, it's not going to be perfect. I think it'll make a mistake. No, maybe it won't make a mistake. So you can see, I also didn't mention this, but up in the top corner, you can see what the actual features are. So they're using sort of a pretty simple model based on the actual sort of like pixelated version of the frame that we're seeing up in the top corner. Oh, actually, it is doing amazingly well. Okay, well, it didn't even fall off, right? So Dagger is this amazing algorithm where Mario Toxicart never falls off.
If you write anything on your computer.
Advertisements. Okay, so what we care to see is sort of maybe going back to our running example of part of speech tagging. This is the results that I presented before, where again, I want to throw tons of caveats on this picture because this was sort of like from the tutorial that was trying to sell Valpal Wabbit. So of course it's doing better than its competitors, but even at the time, the 96.6 up there is not even state of the art for this task. But the point that they were making with this slide was that it was dramatically faster than these off-the-shelf tools for things like conditional random fields, structured perceptrons, structured SVM. All of these are topics that we'll get to later in the course. And so even though I think in practice, these methods actually can outperform this particular learning to search model on this task, they cannot match its speed. And the speed comes from the fact that it's making these greedy decisions. Right? These other algorithms are actually going to be doing, say, marginalization or search over the entire exponentially large space of possible paths. And learning to search is just following a greedy policy through that search space. So it is incredibly fast here. This is another task named entity recognition where it's trying to detect in sentences the occurrences of people or locations or organizations. And again, you see the same sort of trend where learning to search is just doing really well. So this is actually the number of thousands of tokens per second that these methods are giving us. And you can see here that, so on the part of speech tagging task, that 404 would be 404,000 tokens per second. So this is a lot faster than the competitors. Okay, so there's some challenges though. One is that the performance of these algorithms depends really heavily on the search order. So, I mean, why did we tag the sentence from the left to the right? Why didn't we tag the sentence from the right back to the left, right? Well, if you're tagging in Arabic, you should absolutely be doing it in reverse order. The only reason that we did it in English is because we read left to right, so it just felt like the natural thing to do, right? But why didn't I could also do other things. I could have started tagging from the middle and kind of like working my way out. Maybe I could actually identify what is sort of the key verb in the sentence and start tagging there and then worry about all that other stuff around it, right? So, I mean, I just gave you one search order because it felt like the easy one, but there's lots of other options there. And you could imagine that if we were doing something more complex, like reducing syntactic parsing, where we're generating an entire tree down to a linear process, there are even more options in front of us. And so, in fact, one of the examples that we'll get to, probably not this time, we'll get to it next time, is that of sort of state-of-the-art machine translation. And in 2014, there was this use of the sequence-to-sequence models that we talked about, and they realized that it was actually beneficial to decode to basically do the actual search for the sentence that you were translating to in reverse order. Okay? And so the models have sort of since come around to actually compensate for that, and I think maybe we're back to left to right now, but this order is extremely important. Another thing is that the reference policy is critical to success, but what if we don't even know what the reference policy should be? Okay. So, okay, for part of speech tagging, it's sort of obvious that you should just complete the tags with, the correct tags, whatever the beginning tags were, right? Okay, but what if we're doing machine translation, and I give you a nice sentence, and then I give you a partial translation of it. Okay. So, and then I ask you to complete that translation as accurately as possible. Okay. So, for example, maybe the sentence that we're actually trying to translate is something like, could you please give me directions to the nearest train station? Okay. And then the beginning of the translation is something like estación del tren. Okay, and now you need to complete that Spanish translation, but we've already kind of gone down some strange path, right, that puts the actual train station at the front of the translation, and we need to figure out how to complete that sentence in a reasonable way. Having an oracle that does that might not be obvious. And then lastly, this does pose some difficulties for making things efficient on a GPU, which will be important for the deep network scoring functions that we're about to talk about. Okay, so these are sort of learning objectives outlining kind of some of the things that I hope that you'll be able to walk away from this section of the course with the caveat that number 3 is sort of only relevant if you actually already have seen reinforcement learning. Okay, so I want to talk about seek-to-seek, and to do that, we're going to have to step through a number of topics. But I want to begin with the question, why are we going to talk about sequence-to-sequence models? So, it actually took me a while to generate this slide because I had to remember back to 2009 when I was starting my PhD, how people were doing machine translation and acoustic speech recognition. And I say that it took me a while to make this slide because it was so convoluted, the way that we were doing it back then, that it actually, required me to really dig deep in my memory to remember how these actually worked. So state-of-the-art systems for machine translation and ASR had all these different components. So for machine translation, there would typically be a first step that was unsupervised word alignment of sentence parallel corpora. So Giza++ was sort of one of these methods. Once you had words aligned between parallel sentences, the English sentence and say the French translation, then you could build up these phrase tables that were little phrases that kind of translated to each other. The same way that you could imagine having a phrase book for your favorite language when you're going on vacation to, I don't know, Greece and you don't actually know how to speak it. Here, these would actually then rely on all of these other tricks like prefix trees and on-demand loading because these phrase tables would be so huge that they wouldn't fit in memory. And then you wouldn't just represent the words by themselves, you would want other features like part of speech tags and lemmas and morphology, and you would have other systems that were actually feeding into the machine translation system, all of that stuff. Okay. For each of the words in your input sentence. And then you would go off and you would look up, sort of the best state-of-the-art language model at that moment, which maybe was SRILM, And you would build a language model that told you how sentences in French, if we're translating to French, actually look like. Okay. And then you could combine that language model with some phrase-based decoder, and you could train the whole thing via minimum error rate training. Okay. If you're doing ASR, well, boy, you definitely needed to spend a whole lot of time doing feature extraction. I guess you still actually have to do that. But once you had those features, then you would build an acoustic model based on Gaussian mixture models. You would have a phonetic model that was using hidden Markov models. And then you'd have an n-gram language model. 3 separate models, trained maybe entirely separately. And then you would actually combine those in some, say, weighted finite state transducer toolkit like OpenMST, and you would decode from a confusion network, like a lattice from that WFST. Whew. Oh man, this is what we were doing in 2009. Today, we just use a sequence-to-sequence model. Okay, here's how it works. The encoder reads in the input, say 1 token at a time or 1 acoustic frame at a time. And as it's going, it's building up and adaptively changing a vector representation of that input. Okay, at the end, you get 1 vector representing the entire input. Okay. The decoder then starts with that vector that you just produced as context. And it decodes 1 token at a time. So it outputs the first French word, and then it takes the French word that it just output and it feeds it back into itself so that it knows the actual current state. Okay? But the state is actually represented by another vector that is adaptively updated. So we predict the second French word and then feed it back in and update our vector state again. And go down the line until we produce our entire French sequence and we output a special token end of sentence. Okay. And we use this for machine translation. We use this encoder-decoder model for acoustic speech recognition, for image captioning, for things like handwriting recognition, for optical character recognition, all over the place where you're trying to generate a sequence. This sort of simple idea for a model has come to work incredibly well. Okay. But there's a lot of good questions around this area. So one of them is, what do these models actually look like? We'll talk about that. The other is, how do you actually effectively train these models? We've already talked about that. You use learning to search methods. We'll explain how it all kind of fits together as we go. But essentially, these methods are really just fancy models that replace that linear scoring function that we have been talking about up until now. Okay, so to get there, we're going to talk about recurrent neural nets, RNN language models, and then we'll talk about sequence-to-sequence models, and then sort of as part of that, we'll discuss learning to search in the context of seek-to-seek. And at the end, we'll release homework 1, and we'll ask you guys to actually implement in just, a couple hundred lines of code, a simple seek-to-seek model that is able to do acoustic speech recognition on a benchmark data set. And you'll train it in a couple different ways using sort of the standard supervised approach and Dagger and its variants. Okay, so recurrent neural networks. How many of you have actually seen RNNs, let's say in some detail in your intro ML course? Okay, cool. And what intro ML course were you taking, actually? Just so you can shout it out.
Intro to deep learning.
Oh, intro. Was this picture of this course?
Yes.
Is that where most of you saw it? Okay, yeah. And did it, okay, yeah, that makes sense. Okay, so I think for the rest of you, we are gonna kind of go through this a little more slowly. And for you guys who have seen it before, this will be a little bit redundant, but hopefully this stuff is fun. It has lots of pretty pictures, so you won't fall asleep. Okay, so recall we have these data sets that are things like part of speech tagging, handwriting recognition, speech recognition. And in general, what we want to do is we want to work with time series data. So One question is, if you had a neural network that could only take fixed size input and output, how could you model a prediction task with variable length input and output? So what if you wanted to replace that linear model we were talking about for search-based structured prediction with a neural net? What could that look like? Any ideas? Well, one thing that we could do is we could say that this word time is going to give us some vector. Okay? We'll have a vector representing that word time. Okay? Then we'll just feed it into our usual neural network, right? So H1 here is probably some nonlinear function like a ReLU applied to W transpose X1 plus a bias, right? And then Y here is going to be some maybe softmax, okay, over W transpose H1, again, plus a bias. And these should probably be different parameters, so we'll say this is W prime and B prime. Okay. So this is a very, very simple neural network. In some sense, it's actually probably going to do worse than the linear model that we had come up with before, because the linear model looked at the entire sentence. It asked, where was this word in the, positionally in the sentence? What were the tags that had come before? Here, this stupid neural network is really just looking at the current word. Okay, and so then we could do this at each time step to predict the tag for each word. So here, the oddity about this is that if we think about the search space that this results in, say we're going to have scores like 3 here and -3 for noun versus verb, and then think about a search space that then has 3 edges for each of these, like preposition, determiner, noun, preposition, determiner, noun. Well, the scores here on this edge, on this edge, and this edge, 1, 2, 3, are going to be the same as the scores on edge A, B, and C. Right? Because all it's looking at is the current word. Okay, so, well, we could do a little bit better, right? We could connect this up a little bit so that you're not just looking at the current word, you're actually now feeding in maybe the word to the left and right. And if you need, we can have sort of a special start vector here. Okay, so now each of these H's is going to get to look at 3 words. Not bad, right? All right. This is pretty good. Okay, and now maybe we'll be able to do slightly better. Okay. But then you could go a step further. Let's actually just keep drawing pictures here. And you could say, well, here, when I'm predicting, say, this softmax, right? When I'm actually computing that, I presumably have already committed to the first 2 tags, right? So we may not know what this is, right? We're about to predict these 3, so we don't actually yet know what they are, right? Don't think of your training data, think about this at prediction time. But we've already predicted noun and verb. Well, we could feed those in to our hidden state as well. Okay. So now we're looking at the current window of words around us, and we're also looking at the previous 2 tags. Okay, so this is actually a reasonable model. If you built this right now for part of speech tagging, it would work surprisingly well. But it turns out that this still has the same limitation that our linear model did, which is that it can't capture infinite left context. Okay. So here I'm saying you can feed in the previous 2 tags, but if your neural net assumes a fixed size input, then you cannot feed in, just arbitrarily all of the tags that came before you. So a recurrent neural network instead is going to try to give us some representation of the entire context. Okay? And so what we actually do here is we define a neural network that uses the hidden state that was computed in the previous time step. Okay? So let's look at, so the first time step is going to be exactly like that feed-forward neural net that we were just looking at. Okay? And you can see here, HT, in that first time step, HT minus 1 won't even exist. So it's really just going to be some weights times the input x vector plus a bias, and then yt is just that hidden state times a weight matrix plus a bias. But now for time step 2, we do actually have a value for the vector ht minus 1. And so we could say that we're going to compute this vector h2, and it is going to rely both on the value of x, the current word, but also ht minus 1, which is ostensibly going to be a representation of the entire input up until now. Okay. So at time step 3, we're going to feed in h2 and x3 to compute this new vector representation. Time step 4, 5, and so on. Okay. So what we're getting here is this sort of chain of hidden states, where by the time we get to the end, like at state h5, it actually depends on all of the words that came before it. Okay. So to produce our, say, output score vectors, these y's, okay, so actually I guess I didn't pass the y's through a softmax, so I had been writing scores as sort of arbitrary real valued numbers on the edges of our search space. And so that's actually consistent with what we have here, which is that, we're going to take that hidden vector, ht, we're going to multiply it by some matrix, add a bias, and we'll get back some vector that gives us an unnormalized, an arbitrary score for every possible output tag. Okay? So here you can see that the actual vector, yi, is of length k, where k is, say, the number of part-of-speech tags, if we're doing part-of-speech tagging. Okay, so this particular form of an RNN is called an Elman network. And it's sort of as simple as they come. And if you were to use it, you would probably find that it's actually quite difficult to train. It would require some very careful initialization tricks. Otherwise, you might not really have it learn much at all. And but it's nice because it's so simple and clean. And so we can see that if t is actually equal to 1, right, the total number of time steps is 1, then we really do just have that simple feed-forward neural net. And then basically, these are going to allow us to move beyond fixed size neural networks to arbitrary length inputs and outputs. Okay, so to train this thing, we're going to use sort of the usual recipe for machine learning. We have some training examples. We're going to choose a decision function and a loss function. So our decision function is going to be, say, that recurrent neural network. The loss function might be something like cross entropy. And then we'll define our goal to be minimizing the cross entropy on the training examples, where we take the output f theta of xi to be the output of that recurrent neural network. And then we train with stochastic gradient descent, where at each time step we're taking a small step opposite the gradient of the loss of one of those training examples. Okay? So essentially recurrent neural networks are just, some decision function, and they're just another differentiable function. And so when we want to compute the gradient, we can just use backpropagation. Now, the particular sort of form of backpropagation that we use when applied to a recurrent neural network, we often call backpropagation through time, but there's nothing different between this backpropagation through time and just standard backpropagation on that unrolled graph that we were looking at. The reason that we call it backpropagation through time is that another way that you could have sort of visually represented this recurrent neural network was to actually show h as a function of both itself and x. Okay? And under this visual notation, now we actually capture the recurrent nature of the network. Okay? And so to get back what we had before, we would actually have to unroll this recurrent neural network through time. Okay? And so the sort of key point here is that we can actually share parameters across time steps. And that's what is sort of allowing us to accommodate arbitrary length input and output pairs. So there's all sorts of applications of this stuff. We'll talk about those later. But so here's another picture of a recurrent neural network where you can see that BT is a function of both A and then also, but it's also a function of x2. Okay? And those together produce B2, which we use to get x3. Unrolling again, we get B3 and x4, and then maybe at the end some y4. Okay. So this is an old idea that dates back to the 80s. People have known how to do this for a long time. And once you've unrolled this recurrent neural network, you're just running backpropagation through that unrolled network. Okay. So if you want, though, you can now think about how to sort of go beyond that simple Elman network. And you could also have a bidirectional Elman network. Here, now you can see that there's sort of two recurrences, one with an H vector that's going to feed to the right and another that's going to feed to the left. Okay, so unrolling that through time, we can see that the first sequence of H's is going to build up left to right, gradually consuming one input at a time. And then the next sequence is going to consume the input right to left. Okay. And once you have both the right arrow H sequence and the left arrow H sequence, you can use each pair at a given time step to compute the output y. Okay. So why is this nice? Well, if we're outputting, say, a score for each possible part of speech tag, this H3 is going to sort of encode everything about all of the previous words. And this H3, coming from the other direction, is going to encode everything about all of the following words. And so putting the two together and feeding them into Y3 here is going to be some representation of the entire sentence all at once. Okay, so this is just that picture again. Okay. So if you know HMMs, this should look awfully familiar, since it's kind of akin to the forward-backward algorithm. Okay, so we can take this a step further and we can come up with deep recurrent neural networks, which are just going to repeat this idea, but in many more layers. Right, so now the upper layers can have input from, say, the two previous layers. And so whereas, so we could then unroll this through time to get a many-layered recurrent neural network. Okay, so next time when we come back, we'll sort of briefly touch on LSTM cells, which sort of address a particular shortcoming of these Elman networks that we were just talking about. And then from there, we'll move on to thinking about RNN-LMs and eventually seq-to-seq models and how we can actually train them. So, see you all on Wednesday.